Earthquakes and tsunamis are forces of nature that remind us of our planet's raw power. These natural phenomena can strike with little to no warning, shaking the very foundations of our world and altering landscapes in an instant. They strike suddenly, often without warning, leaving behind a trail of destruction. The sheer force of a tsunami wave can obliterate entire coastal communities, while the ground-shaking power of an earthquake can reduce buildings to rubble in mere moments. These events, though terrifying, are essential parts of our planet's natural processes. Volcanic eruptions, earthquakes, and tsunamis are all interconnected through the movement of tectonic plates, which shape the Earth's surface over millions of years. Understanding these phenomena is crucial to mitigating their impact on our lives and civilizations. Scientists and researchers dedicate their careers to studying seismic activity, developing models, and predicting potential disaster zones. While we have learned much about our planet, the ability to predict exactly when and where an earthquake or tsunami will strike remains elusive. Despite advances in technology and science, the precise timing and location of these events continue to challenge experts. The Earth's crust is a complex and dynamic system, and the forces that govern it operate on timescales far exceeding human lifespans. The slow but constant movement of tectonic plates can lead to sudden and catastrophic events when stress is released. We can, however, study past events, monitor seismic activity, and prepare for the inevitable. By analyzing historical data and current seismic patterns, scientists can identify regions at higher risk and help communities prepare accordingly. Scientists have made significant strides in understanding the science behind earthquakes and tsunamis. Through advanced simulations and models, they can recreate scenarios and study the potential impacts of these natural disasters. By unraveling the mysteries of plate tectonics, we have gained insights into the forces that shape our world. The movement of these massive plates is responsible for the creation of mountains, ocean trenches, and the occurrence of earthquakes and tsunamis. These insights, coupled with technological advancements, allow us to develop early warning systems and implement safety measures that can save countless lives. Early warning systems can provide precious seconds to minutes of notice, allowing people to evacuate or take cover. Ultimately, knowledge is our greatest tool against these natural disasters. Education and awareness can empower individuals and communities to take proactive steps in disaster preparedness. By understanding the science behind earthquakes and tsunamis, we can better anticipate their occurrence and minimize their impact. Continuous research and monitoring are essential in this ongoing battle against nature's unpredictability. By heeding the warnings of scientists and engineers, we can design and construct buildings that are more resilient to seismic activity. Community meetings and workshops play a vital role in spreading this knowledge and ensuring everyone is prepared. And by preparing ourselves and our communities, we can reduce the risks associated with these natural disasters. Simple actions like preparing emergency kits and practicing evacuation plans can make a significant difference in times of crisis. We can mitigate the risks and build a safer future for all. Through collective effort, scientific advancement, and community preparedness, we can face the unpredictable forces of the Earth with greater resilience and hope. To understand earthquakes, we must journey deep beneath our feet into the Earth's crust. This outermost layer of our planet is a complex and dynamic environment, composed of various types of rocks and minerals. It is here, in this seemingly solid ground, that the seeds of earthquakes are sown. Here, massive tectonic plates, like pieces of a giant jigsaw puzzle, are in constant, albeit slow, motion. These plates, which make up the Earth's lithosphere, float atop the semi-fluid asthenosphere beneath them. Their movement is driven by forces deep within the Earth, such as mantle convection, slab pull, and ridge push. These plates collide, grind against each other, and pull apart, creating immense pressure. This pressure builds up over time, as the plates are unable to move freely past one another due to friction. When the stress becomes too great, it is released in a sudden and often violent manner, resulting in an earthquake. Most earthquakes occur along the boundaries of these tectonic plates. These boundaries, known as fault lines, are zones of weakness where the Earth's crust is more likely to fracture. There are three main types of plate boundaries: divergent, convergent, and transform, each associated with different types of seismic activity. When the stress at these boundaries exceeds the strength of the rocks, they fracture, releasing energy in the form of seismic waves. These waves propagate through the Earth, traveling vast distances and causing the ground to shake. The energy released during an earthquake can be immense, equivalent to the detonation of thousands of tons of TNT. These waves travel through the earth, causing the ground to shake and tremble. The intensity of the shaking depends on several factors, including the earthquake's magnitude, depth, and distance from the epicenter. Buildings, bridges, and other structures can be severely damaged or even collapse if they are not designed to withstand such forces. The point where the rock fractures is called the earthquake's focus or hypocenter. This is the true origin of the earthquake, located deep within the earth. The depth of the hypocenter can vary greatly, from just a few kilometers below the surface to several hundred kilometers deep. The point on the Earth's surface directly above the focus is the epicenter. This is where the effects of the earthquake are usually felt most strongly. The epicenter is often the location of the greatest damage and the highest intensity of shaking. Earthquake energy radiates outwards from the focus in all directions, causing the most intense shaking near the epicenter. As the seismic waves travel away from the epicenter, their energy diminishes, and the shaking becomes less severe. However, even distant locations can experience significant tremors, depending on the earthquake's magnitude and the geological conditions. Scientists classify earthquakes based on their magnitude, a measure of the energy released. Magnitude is determined using data from seismographs, which record the vibrations caused by seismic waves. The higher the magnitude, the more powerful the earthquake. The Richter scale, though widely known, is no longer the primary scale used by seismologists. Developed in the 1930s, it was the first scale to quantify the size of earthquakes, but it has limitations, especially for very large events. Today, they favor the moment magnitude scale, which provides a more accurate measure of large earthquakes. This scale takes into account the total energy released by an earthquake, as well as the area of the fault that slipped and the amount of slip. It is now the standard for measuring and comparing the size of earthquakes worldwide. Volcanoes, those fiery mountains of molten rock, are also intricately linked to earthquakes. While not all earthquakes are associated with volcanic activity, many occur in areas with active or dormant volcanoes. The movement of magma beneath a volcano can trigger earthquakes. As magma rises through the Earth's crust, it stresses the surrounding rocks, causing them to fracture and shift. These earthquakes, often smaller in magnitude, serve as warning signs of potential eruptions. Volcanic eruptions themselves can also generate significant earthquakes. The explosive force of an eruption can send shock waves through the surrounding rock, triggering earthquakes. Additionally, the collapse of volcanic cones or calderas can create massive craters and generate powerful seismic waves. Understanding the relationship between volcanoes and earthquakes is crucial for communities living near volcanic regions. Monitoring seismic activity around volcanoes provides valuable data that helps scientists predict eruptions and protect lives. Section 4. When humans shake the ground. While the majority of earthquakes result from natural tectonic processes, human activities can also trigger seismic events. These human-induced earthquakes are becoming an increasing concern, particularly in regions with significant industrial activity. One of the primary culprits is the injection of fluids into the Earth's crust, a common practice in oil and gas extraction, geothermal energy production, and wastewater disposal. These fluids can alter the pressure within rock formations, weakening faults, and triggering earthquakes. Mining operations can also induce seismicity. The excavation of large amounts of rock can alter the stress distribution in the Earth's crust, increasing the likelihood of earthquakes. In some cases, the collapse of underground mines can generate significant seismic events. The growing awareness of human-induced seismicity has led to increased scrutiny of industrial practices. Scientists and engineers are developing new technologies and strategies to minimize the risks associated with these activities, aiming to strike a balance between human progress and environmental responsibility. Section 5. Tsunamis. Walls of water unleashed. Tsunamis, often mistakenly called tidal waves, are giant waves that can devastate coastlines. These powerful natural phenomena have the potential to reshape entire coastal landscapes in a matter of minutes. Unlike regular waves generated by wind, tsunamis are caused by underwater disturbances, most commonly earthquakes. These disturbances can also include volcanic eruptions, underwater landslides, or even meteorite impacts. Imagine an underwater earthquake as a sudden jolt to the ocean floor. This jolt is like a massive, invisible hand pushing the water upwards. This jolt displaces a massive amount of water, creating a series of waves that radiate outwards from the earthquake's epicenter. These waves can travel across entire ocean basins, carrying the energy of the initial disturbance with them. These waves travel across the open ocean at incredible speeds, often exceeding 500 miles per hour. Despite their speed, they can be barely noticeable in deep water, with wave heights often less than a few feet. As a tsunami approaches shallower water near the coast, its speed decreases, but its height increases dramatically. This is due to the wave energy being compressed into a smaller volume of water, causing the wave to grow in height. The energy packed into a tsunami wave is immense. This energy is what allows the wave to travel vast distances and still retain enough power to cause significant damage upon reaching the shore. When it makes landfall, it can surge inland for miles, inundating coastal areas and causing catastrophic damage. The force of the water can destroy buildings, uproot trees, and sweep away anything in its path. Not all underwater earthquakes trigger tsunamis. The conditions must be just right for a tsunami to form. The earthquake must be of sufficient magnitude and occur at a relatively shallow depth to generate a tsunami. Typically, earthquakes with a magnitude of 7.5 or higher are more likely to produce tsunamis. Additionally, the earthquake's mechanism, or the way in which the seafloor ruptures, plays a crucial role in tsunami generation. A vertical displacement of the seafloor is more likely to create a tsunami than a horizontal displacement. Modern technology has allowed for the development of tsunami warning systems, which can provide crucial minutes or even hours of warning before a tsunami reaches the coast. These systems use a network of sensors and communication tools to detect and relay information about potential tsunamis. When a tsunami warning is issued, it is vital for coastal communities to act quickly. Evacuation plans and routes should be well known and practiced regularly to ensure that people can move to higher ground safely and efficiently. The aftermath of a tsunami can be devastating, but communities around the world have shown incredible resilience in the face of such disasters. Rebuilding efforts often bring people together, fostering a sense of unity and strength. International aid and support play a crucial role in recovery, providing resources and assistance to those affected. The global response to tsunamis highlights the importance of solidarity and cooperation in the face of natural disasters.